For an ideal gas, PV equals nRT, which is to say that pressure times volume divided by the number of moles, the gas constant, and temperature is always equal to 1. That ratio is always equal to 1. For a van der Waals gas, PV over nRT is not always equal to 1. Instead, the ratio moves along a curve according to the gas's particular values of A and B. The ratio of PV to nRT is called the gas's compressibility factor and is given the label Z. One way to interpret compressibility is as a measure of how far away the gas is from ideal at that particular set of variables, where either the attractive forces or the repulsive forces come to dominate. If the attractive forces, as defined by the constant A, are strong enough, then the molecules will tend to stick together, reducing the actual pressure below the ideal pressure and making Z less than 1. If the repulsive forces dominate, as they tend to do at higher pressures, then the actual pressure is going to be larger than the ideal pressure, and Z will be greater than 1. The balance between the attractive and repulsive forces also determine the gas's phase properties. Molecules like water that are strongly attracted to each other have a much higher boiling point than molecules with weaker self-attraction, like carbon dioxide. It also determines the gas's critical point, the pressure and temperature where a substance loses a distinct boundary between its liquid and gas phase. For example, carbon dioxide's critical temperature is 31.1 degrees Celsius, and its critical pressure is 73.8 bar. When a sample of carbon dioxide is below that point, you can see the boundary between the liquid and gas phase. When the sample reaches or exceeds that temperature and pressure, the phase boundary disappears and it becomes what we call a supercritical fluid. Using the parameters A and B, Johannes van der Waals was able to predict the critical point of gases. In fact, we can define the coefficients using only the gas's critical temperature, pressure, and volume. And if that's the case, then we can really do away with the coefficients altogether. But that's not actually where we're going with this video. The other thing that the critical point gives us is a consistent and physically meaningful measurement of pressure, temperature, and volume. Up until now, we've been pretty agnostic when it comes to units. As long as they're all positive, and as long as the ones you use are consistent, then any unit was as good as any other. The increment size is, after all, a completely arbitrary human invention that has no bearing or meaning on physical reality. Whether we use atmospheres or bar or Pascal and the size of each of these units is just something we made up. So when we construct a compressibility plot based on our made-up units, it's really no wonder that all of the gases behave differently. They have a different curve on the compressibility plot. All that changes when we factor out our units and instead use the gas's own critical point as the unit scale. This is what we call their reduced value, but it's really just converting the units into the natural unit size for that particular gas. The reduced pressure is the measured pressure divided by the critical pressure. So, for example, with carbon dioxide, let's say we have it at 50 bar, with a critical pressure of 73.8 bar. Therefore, its reduced pressure is 0.678, a unitless number. For completeness sake, I'll just mention that you could just as easily convert those values into pascals or atmospheres, or pounds per square inch, or millimeters of mercury, or whatever you want to use. The answer will stay the same. It'll still be 0.678, because the particular units cancel themselves out, and that's really the beauty of it. So what do we get with these reduced variables? Now that we have each gas in its own units according to its own critical point, they're on a scale with physical meaning. We could rightly expect different gases to behave in a similar way when they're similarly near or far from their own critical point. And when we plot compressibility against the reduced variables of pressure and temperature, all the real gases follow the same curve. So by converting our measured variables into reduced variables through the critical values, we're able to map all of the attractive and repulsive forces onto one correction factor, the compressibility factor Z, that tells us exactly how to modify the ideal gas for the real gas behavior under those specific conditions. Instead of PV equals nRT, we can write PV equals Z nRT. And that correction factor is going to put us a lot closer to the actual values that we would expect to see on a gauge than the ideal gas will alone. We'll go through a couple of practical examples on how to use a Z plot in our next video.